Hello everyone. We will represent our research progress on this research, named Evaluation of Threats and Impacts of HD map tampering attacks in autonomous driving. I'm Miyu Sato from Waseda University. First, we will explain HD maps, which are the subject of this study. HD maps are maps used for autonomous driving that contain high-precision 3D information on road information, such as traffic lights, lanes, and crosswalks. The figure on the right shows an example, an HD map. Autonomous driving is composed of various technologies, such as cameras, sensors, and HD maps. Among these, HD maps are essential for safe autonomous driving, as they are used for various functions, such as self-localization to determine the current position of autonomous vehicle, route planning to determine the route and vehicle behavior, and predicting road conditions in areas not visible to cameras. However, if the information on the map is incorrect, it could lead to life-threatening situations. Last year, Google Maps navigation guided drivers and passengers to a crossed bridge that was actually impossible, resulting in a fatal accident. As this example shows, incorrect map information can lead to serious accidents, so it is essential that map information is always accurate. As we discussed, if map information is not updated sufficiently or is tampered with, it could lead to cause serious accidents. The same applies to HD maps for autonomous driving. For example, if HD map information is tampered with in this way, discrepancies between reality and map information may arise, potentially confusing the perception of autonomous vehicles. Therefore, in this study, we evaluated and verified the threats and impacts on autonomous driving when HD map information is incorrect. This study clarifies two research questions. The first is, what security threats do HD map tampering attacks pose to autonomous vehicles? The second is, how do HD map tampering attacks affect autonomous vehicle navigation and planning? The following slides will explain the specific details of each study. First, let's discuss research question 1. This table outlines the risks of HD map tampering categorized by the tampered map element. Building on the 6-layer classification proposed by previous research, we systematically organize the map features, the affect map layer, and the target module and the impact. For example, let's look at the lane feature. This is included in the geometric map and road connectivity layer. If it is tampered with, it can target modules such as mission planner and localization. From this table, our analysis shows that the anticipated tampering content as well as the impact and scope on each autonomous vehicle module vary significantly depending on the tampered element. Now, from the threads we organized, let's take a closer look at an example of an attack targeting lane information tampering. In autonomous driving, the vehicle's driving path is generated based on the lane information provided by HD map. If an autonomous vehicle refers to tampered lane information, it could generate an incorrect driving route. Following this incorrect route could lead to dangerous behaviors such as lane deviation or driving in the wrong direction. For instance, as shown in the figure on the right, an attacker could potentially guide the autonomous vehicle away from the normal light green route and onto the dangerous orange route, which enters the oncoming lane. From the next slide, we will explain in detail a simulation experiment that simulates this specific type of attack. Then we will discuss research question 2. To answer this research question, we conducted an experiment where we expanded the width of the lane on an HD map and then ran the autonomous driving simulation with that modified map. The map we used was an open source vector map of a major city in Tokyo. For the simulation, we utilized Autoware, a popular open source autonomous driving software commonly used in demonstration experiments. On the left, the image illustrates the lane width expansion on the map. We expanded the target lanes in increments of 0.5 meters. The image on the right shows the autonomous driving simulation itself. The video displays the autonomous vehicle's behavior. On the left screen, you can see the route planning, while the right screen shows the vehicle in motion. As you can see, the vehicle is driving into the oncoming lane, which clearly demonstrates a failure in the system's ability to handle the altered lane information. Regarding the experiment's evaluation, we focused on two main areas: analyzing the impact of training and conducting an end-to-end evaluation of the impact of simulation driving. To measure how modifying the lanes affected planning, we set a threshold for unsafe trajectory deviations. The lane width on our HD map is approximately 3.0 meters, and our simulated Lexus has a width of 1.895 meters. To ensure the vehicle stays within the designed lane and does not encroach on the just lanes, we set the allowable deviation threshold to 0.5 meters. This slide shows the results of the fresh distance for both the expanded lane width and the resulting deviation. The blue bars represent the expanded lane width, while the red bar shows the deviation of the planned trajectory from the original route, and the yellow bars show the deviation of the actual driving path. As you can see, both planning trajectory and the driving path danger deviations increase significantly as the lane width is expanded. This clearly indicates a correlation between the two. Furthermore, if you look at the threshold line, you can see that all the deviations exceed this threshold. This simulation demonstrates that autonomous driving systems are highly susceptible to lane width manipulation in the HD map. First, we'd like to discuss the limitations of our study. As you can see, we have three main points. The first point is about the simulation environment. Our research was conducted in a simulation environment using platforms like Autoware and AWSIM. While these are widely used, they may not fully capture all the complexities of real-world driving conditions. Next, regarding the HD map format, we used Autoware's specific vector map format. This means our findings may not be directly applicable to other autonomous driving systems that use different types of HD maps. Finally, the scenario scope. Our evaluation focused specifically on intersection scenarios. The effects of HD map manipulation in other environments, such as highways or residential areas, remain an open question and a topic for future research. In this study, we focused on the threats of HD map tampering in autonomous driving and its impact. We systematically summarized the risks of HD map tampering and conducted experiments and evaluations to simulate lane tampering, which has a high risk. Future work includes evaluation experiments using actual vehicles, tampering with elements of HD map other than lanes, and evaluating the impact in scenes other than intersections. This concludes my presentation. Thank you for listening.